This video describes analog and digital filters used in signal processing. Anyone can imagine a coffee filter or an air filter for an internal combustion engine. The purpose of an air filter in a car is to remove solid particles, dust or sand, from the air, while a coffee filter is used to remove coffee grounds from the drink. This filter effect is based on physical properties, where the desired element must differ from the undesired element in some way. A filter in electrical engineering and electronics modifies certain properties of a signal. It can either emphasize, attenuate, or even suppress certain signal components. Filters in radar are mostly frequency-selective systems that either allow certain frequency ranges of a signal to pass or block them. Filters can work passively, like the bandpass filter shown, as well as contain active components, for example, tuned amplifiers with feedback. The task of a filter is usually to improve, that is, increase, the signal-to-noise ratio of a desired signal. The signal-to-noise ratio, SNR, is the ratio of the average power of the useful signal to the average power of the noise. The signal-to-noise ratio is often specified in the auxiliary unit of measurement, decibel. Note, these are powers. Only voltages can be measured on the oscilloscope. As the impedance of the conductor is the same for both voltages, these voltages can be converted into a power by squaring. As a consequence, this leads to a 20-fold logarithm. This improvement is typically achieved because the wanted signal and noise are in different frequency ranges. The cutoff frequency, or corner frequency, of the filter draws the boundary between the frequency range of the wanted signal and the frequency range of the noise. The cutoff frequency of a filter is where the power level of the wanted signal has dropped to half of its original value. But be careful when evaluating such an image on an oscilloscope. The oscilloscope does not display power, but voltages. Since the amplitudes of the voltages can be converted into a power by squaring, the point for half the power is 0.7071 times the initial value of the voltage. For a filter to be effective, the desired signal and the interfering signal must have distinct frequency characteristics. By setting the cutoff frequency ω0 appropriately, a significant portion of the desired signal can be transmitted while a significant portion of the interfering signal can be suppressed. A low-pass filter is a filter that passes signals with a frequency lower than a selected cutoff frequency and attenuates signals with frequencies higher than the cutoff frequency. The exact frequency response of the filter depends on the filter design. The filter is sometimes called a high-cut filter or treble-cut filter in audio applications. The simplest low-pass filter is a resistor-capacitor combination, a so-called RC element. It works as a voltage divider for the ratio of partial resistance to total resistance and is also calculated in the same way as a voltage divider. The only difference is that one of the partial resistances is the reactance of the capacitor. The cutoff frequency is calculated by multiplying the reciprocal values of the resistor and capacitor. In physics, angular frequency, symbol omega, is a scalar measure of the angular rate, the angle per unit time, of a sinusoidal waveform. It can be obtained by multiplying the frequency f by a full turn, 2 pi radians, omega equals 2 pi f. The high-pass filter has the opposite passband behavior compared to the low-pass filter. In a high-pass filter, the resistor and capacitor are interchanged compared to the low-pass filter. High-pass filters suppress slow changes over time, such as DC components, and trends to extract the variable signal component. The equation for calculating the voltage divider also reverses the positions of the two resistors. Since the upper half of the power should equal the lower half, The calculation of the cutoff frequency is the same as for a low-pass filter. The ideal filter blocks frequency components beyond the defined cutoff, while passing through the signal components without changing their amplitude or phase. The transition between the pass band and stop band should be as steep as possible. Especially if several filters are used in parallel, different phase shifts would have a fatal effect on the subsequent summation. The ideal filter is a theoretical model. It has an infinitely high attenuation in the stop band, but the signal is not affected in the pass band. The transition range between the pass band and stop band is infinitely steep. Real filters do not behave ideally but have different characteristics. It have no ideal frequency response, a continuous transition between pass band and stop band, and some ripple in pass band and stop band. The aim is for the filter characteristic in the transition range to be as steep as possible. The high-pass and low-pass filters mentioned so far are also called Butterworth-filters. Although the British physicist Stephen Butterworth did not invent the filter, as is often claimed on the Internet, he was the first to publish its mathematical description. They are the filters that have the flattest mathematically possible transition range. The diagram shows the filter characteristics of Butterworth filters in a double logarithmic coordinate system. The charge and discharge curves of the capacitor, which normally follow an exponential function, have an approximately linear shape in this coordinate system. A is the function of omega/dB means. Amplitude is a function of the angular frequency omega, measured in decibels. The angular frequency omega is measured in radian per second. A first-order filter has a component with only one frequency-dependent reactance. This means the low-pass and high-pass filters mentioned so far are first-order filters as they only use one capacitor as reactance. When two first-order filters are connected one after the other, a second-order filter is formed. But a simple LC combination is a second-order filter because there are two frequency-dependent reactances, the inductivity and the capacity. A bandpass filter, abbreviated to BPF, is a device that allows frequencies within a specific range to pass through while attenuating frequencies outside of that range. It is always at least a second-order filter. An example of its application is filtering out a specific frequency band, such as in radio or television reception, to extract the carrier frequency of a desired radio station. In electronics and signal processing, particularly in digital signal processing, a Gaussian filter is a type of filter whose impulse response is an approximation to a Gaussian function. Gaussian filters possess some remarkable properties, such as having no overshoot to a step function input while minimizing the rise and fall time. This behavior is closely related to the fact that the Gaussian filter has the minimum possible group delay. Consequently, a Gaussian filter can effectively suppress high frequencies while simultaneously minimizing spatial spread, making it the critical point of the uncertainty principle. Mathematically, a Gaussian filter modifies the input signal by convolving it with a Gaussian function. An ideal rectangular pulse thus becomes a triangular pulse with rounded corners. This is also logical, because the corners of the rectangular pulse mean very high frequencies according to a Fourier analysis, which are blocked by the filter. Technically, the Gaussian filter can be approximated by a resonant circuit. The resonant circuit is formally a second-order filter because it contains two frequency-dependent components. A band-stop filter, also known as a band rejection filter, allows most frequencies to pass through unchanged but reduces the amplitude of those within a specific range to very low levels. This type of filter is the opposite of a band-pass filter. If the stop band is extremely narrow, the filter is also referred to as a notch filter. A digital filter is a mathematical algorithm that processes digital datasets, example given, radar sensor data, to extract relevant information from backscatter and eliminate unwanted data. Digital filters are divided into the following two categories: finite impulse response, FIR filter, and infinite impulse response, IIR filter. As the names imply, each filter type is classified based on the length of its impulse response. Finite impulse response filters are typically selected for applications where a linear phase is crucial, and a reasonable amount of memory and computing power is available. Infinite impulse response filters are typically selected for applications where the linear phase is not critical, and memory is limited. A typical feature of an IIR filter is the feedback path. A finite impulse response, FIR filter, is a filter whose impulse response, or response to any finite length input, is of finite duration because it settles to zero in finite time. The symbols in the figure are: X, N, is the input signal. Y, N, is the output signal. N is the filter order. An nth-order filter has n+1 terms on the right-hand side. Bi is the value of the impulse response at the ith instant for 0 is less than or equal to I is less than or equal to n of an nth-order FIR filter. The Z-1 block is a unit delay. If the filter is a direct form FIR filter, then Bi is also a coefficient of the filter, means the filter order. The figure shows an infinite impulse response, abbreviated to IIR filter, of second order, I equals 2. The implementation of IIR filters is more difficult due to their feedback mechanism. Digital IIR filters have a significant advantage over FIR filters because of their efficient implementation in meeting specifications for passband, stopband, and ripple. They can achieve such specifications with a lower-order IIR filter than would be required for an FIR filter with the same requirements. Digital IIR filter designs come from the classical analog designs and include the following filter types: Butterworth filters, Chebyshev filters, type 1, Chebyshev filters, type 2, also known as inverse Chebyshev filters or Chebyshev filters. Elliptic filters, also known as Cauer filters. The designs of IIR filters vary in the sharpness of the transition between the passband and the stopband, as well as in where they exhibit their different characteristics, whether in the passband or the stopband. The figure in the slide shows the magnitude responses of a typical low-pass filter designed using IIR filter design methods. Each filter has the same numerator and denominator order values. We have already seen the Butterworth filter, which consists of passive RC or LC combinations. Chebyshev filters are analog or digital filters that have a steeper roll-off than Butterworth filters and have either passband ripple, type 1, or stopband ripple, type 2. An elliptic filter, also known as a Cauer filter named after Wilhelm Cauer, is a signal processing filter that exhibits equalized ripple behavior in both the passband and the stopband. A normalized frequency is a ratio of a variable frequency and a constant frequency associated with a system, such as a sampling rate. Type 2 Chebyshev filters, also known as inverse Chebyshev filters, are continuous frequency filters designed to create the sharpest possible bend in the frequency response at the cutoff frequency ω0. To achieve this, the gain in the stopband is not monotonic but has a fixed ripple. Within an order, the larger the permitted ripple, the steeper the drop. In the equation of the gain R, n is the filter order number, Tn is a Chebyshev polynomial of the nth order. Epsilon is the ripple factor, ω0 is the cutoff frequency, omega the actual frequency. Since only the ratio of omega to omega 0 is used, the ratio f to fc can be inserted because omega equals 2 pi f, and 2 pi is shortened. This scale is therefore referred to as the normalized frequency. The filter's cutoff frequency, f equals f0, has a value of 1.0 on the scale. These filters are named after the Russian mathematician Panuty Lvovich Chebyshev. In radar, inverse Chebyshev filters are often used because the ripple is cut off by threshold circuits anyway. The desired signals in the passband, on the other hand, are affected very little. An elliptic filter is a filter with equalized ripple behavior in both the passband and the stopband, that is commonly used in signal processing. This means that the amount of ripple in each band and the selectivity can be adjusted independently. The image illustrates the filter characteristics of a fourth-order elliptical filter with a steep transition between the passband and stopband. Rn is here in the equation the nth-order elliptic rational function. Omega is the actual frequency. Omega divided by omega 0 is the normalized frequency. Epsilon is the ripple factor. Xi is the selectivity factor. Separate videos are provided for more complex filters, such as the matched filter, moving target filter and Doppler filter. Thank you for your attention.